Hello everyone, thank you for joining us at a workshop session of OAI Advanced Cooling Exploration. This is a collaborative work between multiple teams under the OAI group, and we want to share the ideas with wider audience here. In this session, first I will give an introduction to the solutions and challenges associated with OAI cooling. After that, Tianyi from Baidu will share the ideas addressing system-level challenges. In the third part, Ethan from AMD will talk about concept to standardize solution from component level. Finally, I will give a quick wrap-up of current efforts and planning. Just a quick background, we are working under the OAI cooling chapter. We are supporting the development of other chapters from cooling perspective, including both air cooling and liquid cooling technologies. Now let's continue to part 1. What's our mission under the OEI framework? Given the many variations of OEM products and future possibilities, it could be very complicated to design a cooling solution for the OEM products and implement in various platforms. We want to make it easier for potential customers and suppliers by first providing a basic framework so each OEM assembly can be compatible with multiple platforms and vice versa, reducing the number of variations. Second, provide reference designs and guidelines so it becomes easier to develop a new product or derivative product. We hope this might be especially helpful to suppliers who are new to this area. And finally, we want to drive towards standardized solutions which simplifies assembly and logistics management of OEM products, especially for liquid cooling scenarios. You may know that the OEM power delivery is defined up to 700 watts. That's a chance that we may not be able to support all coming OEM products with air cooling. And if we are going to the liquid cooling route, there will be so many complexities we need to address. We have listed some here, and those are the problems we need to solve. So far, we have provided the thermal specification of the OEM product, reference heatsink solution. We contributed to the UVB and the common tray specs, and released a preliminary liquid cooling concept at system level. Now we are diving deep into the liquid cooling area to prepare more technologies to extend the cooling limit. Across the OEM power range, we are preparing following reference designs to support a different power level. If we consider the heatsink cooling limit as 100%, the module level closed loop solution can extend it by 20 to 30%, and beyond which we are enabling couplet loop design to support those. We named those reference designs Tower, Torrent, and Tide. Their simplified drawings should have been shared on our webpage before you watch this presentation. Our target is to explore and improve solutions within system level. It can work with the rack level structures that Open Rack team is developing, which may also be modified depending on the user's infrastructure design. Aside from enabling technologies to cool the high power products, we also see need to standardize the solutions. At system level, there are many factors contributing to the variation and risk of liquid cooling solutions. The effort needed to redesign the customized couplet loops and address the concerns could be very high. It will be ideal if we can define a standard solution for the group, which can support some variations of OEM product and OAI systems. We can optimize it and use it for multiple platforms or even multiple generations. On the component level, there are unique challenges with liquid-cooled OEMs compared to air-cooled OEMs. For different OEM products, you have to prepare the different materials and train people differently for assembly in the factory or servicing in the field. Also, such products typically have multiple types of thermal interface materials involved in this. It could become very difficult and risky to assemble in regular conditions. We are thinking of standardizing the liquid-cooled OEM products so that the assembly can be simplified, and people can reuse the same couplet loops for different products. Okay, Now let me pass it to Tianyi for the next portion.
Thank you, Chang. Now I will be talking system-level cooling, challenges and solutions. I will first give you a brief introduction of our work on liquid cooling, as well as the liquid-cooled Aoms products. Then I will be presenting some of the challenges and the problems we think are critical to be solved in this area, and then give you some of the solutions and the proposals we would like to contribute to the open community and collaborate with the community. This page shows our GPU system Aoms series. We started to implement liquid cooling solutions since Aoms 2.0 in 2017. And start from this 3.0 system, we considered a standard design for an open ecosystem. And the latest version, 4.0, is an OAI compatible design. Some more details about liquid cooling Aoms 2.0. It's an open loop design. So together with the liquid cooling Aoms 2.0, we have developed the facility level solutions for operating this liquid cooling Aoms systems in our data centers. This involves many design efforts and verification tests to ensure the proper performance and reliability. In terms of the reliability, such as whitened material and fluid compatibility, fluid leak detection design were considered in this version. Actually, we have designed and implemented different thermal solutions for Aoms 2.0, the air cooling ones and the liquid cooling ones, for different use cases and facility environments. Moving forward, in the new version Battle-Rack V3, this one considers a high flexible design. The new version supports both 21-inch and 19-inch servers. Different power delivery solutions including bus bar and PDU. In addition, the rack is assembled with liquid cooling manifold for distributing fluid to the liquid-cooled equipment. There are several experience and lessons learned from our previous work in designing and deploying the liquid-cooled Aoms 2.0, and we would like to share with the community. One of the important experience I would like to present here is some of the common challenges and problems we think need to be addressed before this technology can be deployed in scale. These challenges are reliability, including the material, hardware, and fluid long-term reliability, design for serviceability, manufacturability, and productization, ecosystem, and use cases. In terms of addressing the ecosystem challenge and the part of the use case challenge, this is one of the key objectives and efforts within the OAI group. We have started the collaboration and we are contributing our designs and solutions to the group. Here, this one shows our new GPU system 4.0. As mentioned before, it's an OAI compatible design. In terms of addressing the other challenges I just mentioned in the previous page, here are some of the ideas for developing effective and feasible solutions. For example, considering a design like this, one complete system module from a component level to a server level includes multiple cold plates for the OEM. With this system level design idea, considering if water and electronics can be separated for reliability improvement point of view, considering serviceability, ease of installation, fast assembly, less requirement on chassis design, and so on. There may be some other potential benefits from this idea. However, there are still several new challenges need to be addressed before a complete mature solution or product. Here, we would like to work with our OAI partners to address all these challenges. This drawing gives you a basic idea on the full liquid cooling module proposal I just mentioned. All the major components, including the cold plates, hoses, distribution units, connectors, and so on are packaged as one liquid cooling module as component number 4, as well as the mounting brackets if there is any. These figures give the simplified representation of the concept introduced in this proposal. The left-hand side shows a top view, and the right-hand side shows a side view. You can see multiple cold plates are arranged and connected either in a parallel or series manner. Together with the fluid hoses as well as other parts are all assembled within the module. With this design, it may make the solution easy for installation. Also, it provides a certain separation of the fluid and electronics if there is any leak. We would like to collaborate within the OAI group and work with our partners. And we would like to hear feedback from you regarding the proposal and work together developing the standardization specification. The scope of work covers the level 1 cold plate module to a level 2 server cooling module. The standardization is targeting on covering all the items we are listing here in this table. You can see all the key components as well as the entire module. Thank you for your attention. Now I will hand it over to Ethan.
Thank you, Chen Yi. This is Ethan Cruz, and I will now walk you through the concepts for standard liquid cooling section of this presentation. First, I will show the air-cooled heatsink design. Then I will discuss the different heat spreader options. I will then present the heat spreader concept, finishing with its benefits and drawbacks. The air-cooled heatsink from top to bottom is comprised of the heatsink, the top stiffener, the OEM board, and finally the bottom stiffener. Air cooling can support a broad range of products and power levels. Liquid cooling can, in general, support higher power products. There are 3 liquid cooling construction options. I have broken them down by where the cold plate is located, and then by how the module is constructed. The first option is to have the cold plate directly attached to the OEM. In this case, the cold plate is part of the module and can be directly attached to the die. However, this requires that the liquid cooling loop cannot be tested until the OEMs, with their attached cold plates, are installed into the loop. This requires additional care when testing the liquid cooling loop and creates additional risk when replacing OEMs in the field. The second and third options both have the cold plate as part of the system cooling loop. This eliminates the additional risk of removing and inserting a part of the cooling loop in the field. The second option exposes the OEM die to the cold plate. From a thermal standpoint, this gives the best performance by eliminating the heat spreader from the stack-up, but this creates additional risk of an exposed die. The third option adds a heat spreader to the stack-up. This is the concept that I will now present in more detail. The heat spreader concept from top to bottom is comprised of a heat spreader, OEM board, and bottom stiffener. This concept benefits from an ease of assembly and disassembly within a server. It reduces the risk of damage to the silicon package. It also allows for universal cold plate mounting, which could be used for multiple generations of products and even across different OEM suppliers. It also provides for cooling of other components on the OEM board. This concept does have some drawbacks. First, it does add a thermal interface compared to the direct die access designs. It also adds thermal resistance for the other components on the OEM board as compared to a cold plate specifically designed to touch those components directly. The major drawback to this heat spreader concept is the thermal performance degradation compared to the other direct die attach options. Although the thermal resistance from the die surface to the coolant inlet is slightly increased, it still can provide a significant improvement over an air-cooled solution. The graph on the right shows the heat spreader concept adding about a 15% increase in thermal resistance compared to the direct die access concepts. However, this is much lower than the air-cooled thermal resistance shown at over 50% increase in thermal resistance. The heat spreader concept can also provide better heat spreading for the other components attached to the OEM board. In summary, the heat spreader concept outlined here can potentially cover the entire OEM. Since there is not a direct attachment of the cold plate to the die, there is potential to use better thermal interface materials to the die. It also provides easier cold plate attachment that could potentially be universal. And it does not require the liquid cooling loop to be broken, since the loop can stay inside the system. There are no quick disconnects or required breaks in the cooling lines for this concept. This concept allows for a universal cold plate design with a common OEM attachment method. This not only allows for the same cold plate to be reused for different OEM generations, but also across different suppliers' OEM designs. The cold plates could also be greatly simplified to further reduce costs. I will now hand it back to Cheng.
Thank you, Ethan. I will continue to the ongoing efforts and planning. Like I mentioned above, there are unique thermomechanical interfaces between each OEM product and their heatsink or cold plate solution. This makes them very complicated to assemble and service for customers and system integrators. Sometimes it could take 10 to 20 minutes to clean and reapply the thermal interface materials, but a tiny mistake could easily damage the silicon, like the picture showing on the right side. If you look at the original OEM spec, we have standardized the OEM bottom interface, so it's identical for mounting to baseboard. To make it identical for cold plate, we also want to propose standardizing the OEM top interface. Just to refresh your memory, we have presented multiple options in the regional summit last year, and after studies in the past half, we prefer the lead cover option as Ethan described. This is a list of pros and cons we described last year. It's only a high-level analysis. By having a standard lead interface design, we can use a universal cold plate to support different OEM products. It makes the assembly much easier and avoids damaging the bell die. This is a checklist of items we are working on, which eventually will become an OAI liquid cooling spec. For those who are interested or have need of liquid cooling OEM, please join us and develop the spec together. Finally, some links for your reference. And this is the end of our presentation. Feel free to comment if you have any questions.